Hello and welcome to MATLAB programming for numerical computations. We are in module 6. In this module, we have been covering regression and interpolation. In the first lecture of this module, we covered introduction to regression and interpolation. In the previous lecture, we covered linear least squares regression and took up an example and solved it using a matrix method for linear least squares. In this lecture, we are going to take a physically relevant example and show how we can do linear and nonlinear regression. We will take example of rate of reaction, the Arrhenius form that we have studied in our 11th and 12th grades. We will take an example for the Arrhenius form and show how we can use linear or nonlinear regression in order to obtain the parameters for the rate of reaction. So the Arrhenius model for reaction rate is given by rate R equal to K naught multiplied by e to the power minus E by RT, where E is the activation energy and R is the gas constant, multiplied by concentration C to the power N. So K naught multiplied by e to the power minus E by RT, C to the power N. Now we will solve this problem in two different ways. First is using linear least squares regression. Now this is clearly not a linear form of equation. You see, you have your K naught, you have the other parameter is E by R and the third parameter is N. They are not related to each other in a linear fashion. However, if we take a logarithm of this, we will get logarithm of R equal to logarithm of K naught plus negative E by R multiplied by 1 by T plus N multiplied by ln of C. So if we were to write 1 by T equal to X, we were to write ln of C equal to U, we will get this in the form Y equal to A naught plus A1 multiplied by X plus A2 multiplied by U, where our A naught is nothing but log of K0, our A1 is nothing but minus E by R, and our A2 is nothing but our N. Okay, so this has a form which is linear in the parameters that we are interested in finding. Note that when we talk about linear regression or non-linear regression, we mean that it is linear in the parameters or non-linear in the parameters respectively. It doesn't matter whether it is linear or non-linear in the measured quantities, that is in this case temperature, concentration and rate of reactions are measured. It doesn't matter whether it's linear or non-linear in these quantities. What is important that is that it should be linear in A0, A1, A2 and so on. It is indeed linear in A0, A1, A2. So first we will solve this particular problem using linear least squares, and then we will solve it using non-linear least squares using the MATLAB function lsqnonlin. lsqnonlin is a function that is available in MATLAB's optimization toolbox. So you will have an access to that function only if you have access to the optimization toolbox. So let's go ahead and solve this problem in two ways for the following data. So the data is obtained at 5 different temperatures: 400, 450, 500, 550 and 600 kelvins, and 4 different concentrations: 1 mole per liter, 2 moles per liter, 3 moles per liter and 4 moles per liter. And this is the rate of reaction given in moles per liter per second. If we take the logarithm of the rate, we are going to get the expression of the form y equal to a naught plus a1x plus a2u. Okay, so y is log of r, x is 1 by t, and u is log of c. And that's what we will use in order to do the linear regression. Let's go to MATLAB and do that. Okay. So what I have done already is written down a snippet of code for obtaining the data in concentration and temperature. So let's see what data that we have. So when we run this, I have given a command to display x data and y data, and let's go ahead and do that. Okay. So this is basically our uh, independent variables concentration, independent variable temperature, and our dependent variable rate of reaction. Let's look at the table that we had. So for 1 moles per liter and 400 kelvins, it was 1.48. For 2 moles per liter, 400 kelvins, it was 2.35. For 1 and 400, 1.48, 2 and 400, 2.35, 3 and 400, 3.28. For 3 and 400, it's 3.28, so on and so forth. So the temperatures are given as uh, X data 2 and concentrations are given as X data 1. The first column is concentrations, the second column is temperatures, and Y data is nothing but our uh, rate of reactions. Okay, so what we want to do is get our X is nothing but 1 by T, our U is nothing but log of C. So let's go ahead and do that in MATLAB first. Okay, so let me delete this line. As the instruction says, delete this line before running the code. The reason why I had this line over here is to display to you what the data looks like. Okay, so our concentration is going to be, um, excuse me, uh, yeah, our concentration is X data column 1, our temperature is X data column 2. What we first need to do, we want to call our X as 1 divided by T. So X equal to 1 dot slash T, and T is X data, all the rows, second column. Okay, that's our X. Our small u is the first column of X data, logarithm of that. For u is logarithm of C. C is the first column of X data. So u is going to be logarithm of our concentrations. Concentration is nothing but X data, all the rows, first column. Okay, so that's our X and U. Our Y is nothing but logarithm of rate. Rate is in Y data, and our Y is nothing but logarithm of rate. So we will put that in log Y data. Okay, so let's run up to this stage and see whether we have X, U, and Y correctly, or if there's some error, MATLAB will throw us an error. Okay, so there's no error. So X, U, and Y has probably been obtained correctly. Let's look at our X. X is 1 by temperature. So we should be getting 1 by 400, 1 by 450, and so on. So let's type X and see what the values are. So 1 by 400 is 0.0025. 1 by 500 is 0.0020. So this looks like it's correct. Okay, so we have our X, we have our U, we have our Y. So let us construct our big matrices. Our X was nothing but ones, and that is size of n rows and single column. Then we had our X followed by our U. Okay, this should give an error. I'll come to that in a minute, but let's say Y was nothing but our Y. Okay, so let's run this and see whether we get an error or not. Yes, we get an error, and the reason why we got an error was because our variable n was not defined. Okay, so again, I'm going this in a step-by-step manner so that this becomes fairly easy for us to debug. So every time I write a few lines, I will go back and check. You don't need to do that. You can write the entire code and then check it. The reason why I'm doing this is basically on a video like this, it becomes easier for me to go and show you where the errors can possibly be rather than typing out the entire code. Okay, so it's up to you how you want to do this, whether you want to do this in a single shot, writing the entire code and then debugging it, or writing few lines of code, running it, and then check whether the results are okay or not, and debug if whenever you get an error. So anyway, the error was that n is not defined. So let's define our variable n over here, n equal to length y. So n is the number of rows in our vector y. Okay, so this is our x, this is our y, and our phi is going to be nothing but inv of x transpose multiplied by x multiplied by x transpose multiplied by y. Okay, that was how the way we do linearly squares. It was x transpose x inverse x transpose y. So inv of x dash multiplied by x. Our k naught is exp of a0, that is phi 0, sorry, phi 1. A0 is phi 1, right? Okay, so this is how our phi 1 is going to be nothing but logarithm of k0. So k0 is e to the power phi 1. E by r is nothing but negative a1. So e by r is minus phi 2. And oops, let's get to PowerPoint. And our n is nothing but phi 3. Okay, so that's our linearly squares. Let's save and let's run this. Hopefully it will run without an error. Okay, we have run this and our E by R is 480.1, K naught is 4.8, and our N is 0.75 approximately. So that's our rate of reaction using linearly squares regression. Next, what we are going to do is we are going to use nonlinear regression of this particular function directly using lsqnonlin. So let's look at the syntax for lsqnonlin. The syntax for lsqnonlin is phi equal to lsqnonlin at phi space function name phi and the initial guess. So let's start with that. Okay, let's say our initial guess for phi naught, phi 0 or phi guess, let's say was 1 was our k naught. Let's say our E by R was 100 and our N was also 1. So let's say that was our phi guess. Okay, our phi non phi LSQ is going to be LSQ nonlin at phi, let's say RxN function phi. Okay, so this is the standard syntax. We need to define our function called RxN function and our phi guess. And I think that should be, yeah, that should be all that is required. Now, the function f provides errors in the form of e equal to y minus the model for various values of phi. So we basically need to get that in our function. So let's go here, edit rxn function. Yes. Okay, so function f error equal to rxn function and our phi. Okay, so our k naught is phi 1, our e is phi 2, and our n is phi 3. Rate of reaction is going to be nothing but k naught multiplied by exp minus e by rt, so minus e. So e over here we are using this for e by r. So e by r dot slash t okay, multiplied by concentration C to the power n. Okay, that the final bracket was not required. It's just for our sake, for human readable sake. So that's rate of reaction, and our F error is nothing but Y data minus R. Okay, so to get parameters, calculate rate. Okay, so before that we need to get what C is. C is nothing but our X data, all the rows, first column. T is X data, all the rows, second column. Okay, so again, when I run this, I'm going to get an error. So let's see what the error is going to be. Okay, let us run this and we get an error. Okay, the error is undefined function or variable x data in rxn function. The reason why we get this error is x data and y data are defined in our workspace, but this is a function. They are not defined in our function. We need to somehow pass on this information in the function. So let's put this as two parameters, two additional parameters of the function. Okay, so x data and y data need to be passed on to the function by the reacts param script. Okay, and the way we do that, we know how to do this, is we have at phi, so that's the variable we need to solve for, and in rxn function, in addition to phi, we pass on all the other parameters that's required. X data, Y data. Okay, keep in mind X data and Y data over here stand for this variable name and this variable name. The X data and Y data over here stand for basically the variable name that we are going to use over here and here. They happen to be the same variable names because it's the exact same data, but it need not be that. I can actually replace this with just, let's say, xx and yy, and that will also work. Okay, x data, y data will also work, and xx and yy will also work. So let me just save this and run this and see that it works. Hopefully it should, without an error. Oops, there is an error. Okay, the error isn't with the multiplication in line 11. And we wanted an element by element multiplication, so we should have put a dot star there. K and star is fine because k naught is a scalar. So let's clear all and run this. Okay. Okay, so it's run, and let's see what phi lsq gives us. So with phi lsq, we got our k naught as 4.84. Our E by R is 486, and our N is 0.75. Okay, so we are getting very close numbers using our LSQ nonlin as well as using our linear regression. Okay, let's go over here and see what we have done again. Okay, lsq nonlin at phi rxn function phi comma x data comma y data. The name x data over here has to be the same as this name over here. Y data has to be the same as this name over here. Phi has to be the same as this name over here. Okay, so let's change this data to x data and y data. So everywhere we have changed this to x data, everywhere we have changed this to y data, and let's run this. Okay, and it runs with our phi lsq as the same values as before. So as you can see, the variable names are dummy. As long as this name is exactly the same as this name and this name is exactly the same as this name, there is actually not going to be any error that you will see. Okay, so with that, we have completed our aims of this particular lecture. Our first aim was to convert this into a linear regression form and use linear least squares. And our second aim was to use non-linear least squares using MATLAB function. Okay, with linear least squares, we use matrix method and created that matrix. The Y matrix was log of R. The X matrix, the first column was ones, the second column was 1 by T, the third column was ln C, and we use that in order to get our log of K naught, our E by R and N. Then we used MATLAB function lsqnonlin, the standard syntax for which was phi lsqnonlin at P f name P comma P naught, where P naught were the initial guesses. Okay, and if there were parameters, then we changed this to at P f name P comma param 1 comma param 2 and so on and so forth. F name returns the vector of errors, which is y minus y model. Which y is nothing but r minus the right hand side. So this is the error as a vector that fname needs to return. Okay, so with that we come to the end of lecture 6.3, and I will see you in lecture 6.4. Thank you and goodbye.